All right, guys, this is your study guide help video here. So I'm just going to go ahead and go through the study guide, and we'll see how you guys do. All right, so for the first one here, let's look at our instructions real quick. It says, for each problem, determine if the MVT, that's the mean value theorem, or the EVT, the extreme value theorem, can be applied to these functions on the interval provided. Okay, so on your quiz, you would get 1 point for getting it correct and 1 point for your explanation. All right, so let me back up. That's the wrong question. There we go. So for the MVT to apply to this problem on this interval here, it needs to be continuous on the interval -3 to 1, and it needs to be differentiable on the open interval -3 to 1. In order for the EVT to apply, it only needs to be continuous on the closed interval. And that's it. Okay, so how are we going to determine whether it's continuous and or differentiable on that particular interval? Well, first of all, you need to identify what kind of a function is this. Once you know what kind of a function it is, you can go ahead and look at your continuity of common functions worksheet that I gave you back in Unit 3, Lesson 3.3. It's in Week 10 in case you guys need to find it again. But this function here, if you want to rewrite it a little bit, is actually a cube root function, which is being squared. Okay, that's what a 2/3 power is. It means you're taking the cube root of a function that's being squared. Okay, so it's a cube root function, and since it is primarily a cube root function, we would look here at radical odd roots, and what we would discern is that they are continuous everywhere. So they never have any discontinuities. Okay, so this thing is in fact continuous everywhere. And since it's continuous everywhere, that means that it is continuous on the interval -3 to 1. Which means that for sure the EVT applies, because that's all that's required for the EVT to apply. Okay? Now, in order for the MVT to apply, this has to be true, but we need to go a little bit further. We also need to find the derivative. Okay, so let's find the derivative of this. So to find the derivative, I'm going to take this power and I'm going to move it to the front. So it's going to be -2/3. And then I'm going to subtract 1 from the power, which is going to make it -1/3. And then you multiply it by the derivative of the inside, because this is a chain rule, so times 1. Okay, now I'm going to clean this up a little bit. First of all, if you multiply the 1 times the -2/3, you just get 2/3 still. And then this little -1/3 is actually going to throw the x minus 1 into the denominator. So it's going to look like this. The -2 is in the top, and so is the 3. And now the x minus 1 is going to go in the denominator with a 1/3. Now, as soon as you get something in a denominator like that, you have a discontinuity somewhere. Okay? The discontinuity, at this point, this is a cube root function, but it's also kind of like a rational function, because it's a fraction. And when you have rational functions, they are discontinuous anytime the denominator is equal to 0. Okay? So as soon as you get a fraction involved there, you have a discontinuity, and it happens when the denominator equals 0. So what would make this denominator equal 0? Well, all you have to do is you have to take the factor with an x in it, set it equal to 0, and solve, and it will tell you where the discontinuity would be. We have a discontinuity then at x equals 3. But that's not necessarily a problem. The question is that on our interval? Now when you're doing the MVT, if you're trying to see if it's differentiable, the first thing you do is take the derivative, you find where the discontinuities are for that derivative, and then you check to see if those discontinuities are on this interval. And remember, when you're doing differentiability, it's open parentheses. In other words, we don't care. It wouldn't matter if I had a discontinuity at -3 or if I had a discontinuity at 1, because this is an open interval. Whereas up here, since it's a closed interval with the brackets, we do care. But down here, it's okay. Now in this case, is the number 3 on the interval from -3 to 1? No, 3 is not on that interval. So since there's only one discontinuity for this function, it's at x equals 3, and that discontinuity is not on this interval, then we can go ahead and conclude that it is therefore differentiable on the open interval. So even though it does have a discontinuity, that discontinuity is not on the interval we care about. And since it satisfies both of these, then yes, the MVT applies. Okay, so how would you, what kind of work am I expecting for you guys to show on your quiz? Well, for continuity, on this problem, there really wasn't a whole lot of work to show. You just needed to state the fact. Just make the statement that yes, it's continuous on the interval because it's right on the worksheet there. For the differentiability, I would expect to see a derivative. And then I would expect to see the statement. Okay, so you need to find your derivative, and from there you can make your determination about whether or not it's that. But your final answer will have to include something about, it would have to look like this. Since it's, well, we don't say it's in this class, so I want to avoid that. We always want to be specific. Since the function is continuous on -3, 1 and differentiable on the open interval -3, 1, it is, well, actually we should say both MVT and EVT apply. Okay, so I would want to see your work for finding the derivative, and then you have your answer basically. Okay, so that's basically it. I'd want to see for sure these two things, the derivative and then this statement on your quiz. All right, let's go ahead and move on to the next one. So for this one, I'm going to go ahead and let you guys do that one on your own, and we'll move on to number 3. Number 3, let's go ahead and begin. Once again, we need to see, is it continuous on this interval, and is it differentiable on this interval? And once again, we're going to start off with looking at our sheet for continuity of common functions to decide whether this is a continuous function or not. Now that's a rational function. So when I come over here to this thing, since it's a rational function, the denominator cannot equal 0. That would be where a discontinuity would occur. So all I know is that 2x plus 2 is not allowed to equal 0. So let's go ahead and solve it and see what x is not allowed to equal. Oops, not negative, my bad. So x equals -1. So we do have a discontinuity at x equals -1. But is it on the interval? -4 to -2. No, it's not. So it's continuous on -4, -2. Now we want to see, is it differentiable? So now let's see if it's differentiable. Step 1, derivative. So this is a rational function. When it comes to rational functions, the way that you find the derivative is you do low d high minus high d low. Draw a line and square below. Okay. Now you are going to want to, well, actually, it's probably not entirely necessary to simplify this problem at this point, so we can probably just leave it. It's still a rational function. Okay. So what we can do is we can find, look for the discontinuities for this derivative. Now, if the derivative is discontinuous at a certain point, then that means that the original function is not differentiable at that point. Okay? So, well, we have the same kind of function. It's still a rational function. And so the denominator, which is really the same denominator, can't equal 0. And we already solved this earlier. We found that that means that x cannot equal -1. So not only is the original function not continuous at -1, but the derivative's not continuous at -1, which means that the function is not differentiable at -1. But once again, is that on the interval that we care about? From -4 to negative, I left a negative off there, that's kind of important. Is -1 on the interval, open interval from -4 to -2? No, it's not. So we're good. So this function only had one place where it wasn't differentiable, it was at -1, but that's not on our interval. So the function is differentiable on the entire interval that we care about. So we would say, once again, both MVT and EVT apply. And once again, what do I want to see on this on your quiz for your work? I need to see the derivative, and I would also need to see the fact that it's continuous on that interval and differentiable on the other interval, and then your statement about the fact. Okay. Now, the reason why I'm not saying you guys have to show your work here is because, honestly, I figure a lot of you guys could probably do that mentally. So I don't care if you show your work on solving for x. Now, there may be some problems where you would actually need to. You know, it's kind of, I shouldn't see too many magical things, but I imagine you guys should be able to solve 2x plus 2 mentally. But, you know, if you want to show your work just to be careful, you can. But once again, I would want to see the derivative for sure, and then I would want to see this. Now, in the last problem, I wrote it as a sentence where I included the top part and the bottom part together as one. But so long as those pieces are there, I don't care how you really write it. But I need to see the derivative and then those two things on the right there. All right, so now I'll let you guys do one like that on your own, number 4. Let's move on to number 5. So this is an absolute value function. Let's go ahead and see. Well, first of all, absolute value functions are continuous everywhere. So let's see if we can find one here. Do I even have one on here? Nope, I don't have one on here. But I'll tell you now in our video, they are continuous everywhere. So, to answer the question, is y continuous on our closed interval 0, 4? The answer, therefore, would have to be yes. Now, just as a just as a side note, not something you really need to worry about in this particular quiz, but as a side note, absolute values functions are continuous everywhere. But if there's another kind of function inside of it that has a discontinuity, then that still has a discontinuity on it. But this is a polynomial, so polynomials don't have discontinuities either. Okay, and same thing goes for any of these functions. A lot of these functions we're looking at are actually complex functions where you have multiple types of functions put together. But so long as every piece in there is continuous, then you're good to go. But I would primarily classify this problem as an absolute value function. That's the outermost function. All right. So it's going to be continuous because absolute value functions do not have any discontinuities. Now let's go ahead and take a look at the differentiability. First of all, we want to do our derivative. When we're doing differentiability, it's open. Is y differentiable on the open intervals 0 to 4? Okay. Now, another way you could ask that question, in case you guys haven't already, hopefully you guys have already gotten this, but if not, the way you tell if y is differentiable on the open interval is you ask yourself, is y prime continuous on 0, 4? That's the same question, just asked in a different way. Okay, so asking is y differentiable on the open interval is the same thing as asking is the derivative continuous on the interval. So step 1, of course, then is to find the derivative. So you guys need to remember how to find the derivative of an absolute value function. So let's start here. The derivative of that is going to be as follows. When you take the derivative of an absolute value function, you put the original function on the bottom, and then you put whatever's inside of it on the top, and then you multiply it by the derivative of the inside, which is 2x. Okay, then we have our -1. The derivative of that is 0, so it just goes away. And so that is our derivative right there. Now, once again, since I've done this, we end up with a, we still have an absolute value function, right? And we still have polynomials, right? But the outermost function at this point is a rational function. And once again, rational functions have discontinuities anytime the denominator is equal to 0. So is x squared minus 4, can it equal 0 anywhere? Well, if I add 4 to both sides, and then I take the square root, it actually has two discontinuities, positive and -2. Are either one of those on the interval from 0 to 4? Yes, it is. 2 is on the interval. Positive 2 is on the interval from 0 to 4. So we have a discontinuity for the derivative on the open interval 0 to 4, which means that y is not differentiable on the open interval from 0 to 4. So therefore, y is not differentiable on the open interval 0 to 4. Okay, now what would I want to see for a problem where you can actually find where there's some discontinuities? Well, some things that I would expect to see is I would want to see the statement that y is continuous on the closed interval 0, 4. I would want to see that. I would want to see the derivative of y. Right here, this thing. And for this particular problem, you don't necessarily have to show the work, but I would definitely want to see where you have the discontinuity. So you can say y is not differentiable on 0, 4 since there's a discontinuity at x equals 2. That would be fine if you just want to add it to that sentence. or you could just show your work over here. But I would want to see somewhere that you found, I want to know what is that discontinuity. It's 2, right? So that's another thing I'd want to see. And then finally, I'd want to see this. Well, that's not actually finally. And at that point, we need our conclusion. So we would say, therefore, EBT applies. But MVT does not. Okay? So, now a much nicer way to write your final answer would be to say, since y is continuous on 0, 4, but not differentiable on 0, 4, EBT applies, but MVT does not. Okay, so that would be that's how I'd love to see you guys write your final answer. But so long as you had all those parts on the last one, then I'm glad to give you full credit anyway. Just make sure it's nice and neat and easy to read and follow. All right. So the next question I'm going to let you guys do, and these sets of problems here are basically just meant to see can you know when the EBT and MVT can apply. Now a little heads up for this guy here, you're going to need to set that equal to 0, and the way that you're going to want to solve that is by factoring. So I'll let you guys take that one from there. But anywho, that's whenever you get to the point where you're going to see if it is differentiable. For continuity, you shouldn't have a problem with that. Anyway, let's go ahead and move on to number 7 here. I need to get out of here so we can actually see the instructions. What do they want us to do on number 7? Number 7 says, for each problem, find all the points of the absolute minima and maxima on the given interval. So there's a process that we're going to go through, but I tell you how you're graded here. 1 point for finding the derivative, 1 point for finding the critical values with work shown, and 1 point for actually doing the EBT table, and 1 point for identifying the correct answer. So these ones are worth a lot of points. You want to make sure that you show all your work, and including those 1, 2, 3, 4 things in particular. Okay? All right, so let's go ahead and get down to business. Right. So when we did these problems earlier, we'll get to the right question here. When we did these problems back in lesson 5.2, the first thing we did was we wanted to make sure that the EBT applies. But for this quiz, we don't have to do it. The reason for that is because I'm only going to give you questions where the EBT will apply. So you don't need to show any work for proving to me that the EBT applies. I'm not counting that worth any points. Why not? Well, that's what questions 1 through 6 were all about, was you showing me that you know how to determine whether or not the EBT applies to a given function. Okay, so we're not going to worry about the first step. And I'm going to promise you that the functions that you have on your test, the EBT will necessarily apply. So we're going to skip step 1. Step 2 is to find the critical values. Now, critical values are where the derivative equals 0 or where the derivative is undefined. Okay, so let's find the derivative of our function up here. Y prime would be negative 3x squared minus 2x plus 1. And at that point, we're going to set it equal to 0. and we're going to solve. Now, at this point, you can use quadratic formula or you could do factoring. I like to try factoring first, so let me give that a shot. All right, and so it turns out that this one does indeed factor, so we're good. Let me make a little more space for myself here. And then we're going to set each piece equal to 0 and solve. I'm not going to show my work here. I'm just going to go ahead and get the answer. You would get 1/3, and you would also get -1. Okay? So now, once again, we only care about critical values that are on the interval we care about. So I only care about critical values that are on the interval from -2 to 1. Now, both of those are on the interval. Now, where would the derivative be undefined? Well, since my derivative is a polynomial, the derivative is not undefined. And therefore, there are no critical values here. So we only have two critical values. They are 1/3 and -1. All right, so the next thing that we do is we go ahead and set up our table. Now, you always want to start with your endpoints. So put your lowest endpoint on top, your highest endpoint on the bottom, and then squeeze these in between in order. The reason I advise you to do that is because sometimes if you forgot to make sure that these critical values are actually on this interval, at this point, if you follow that process, you'll catch it, okay? So I know that the next number would be -1 and then 1/3. And if I ever ended up with a critical value that didn't fit in between -2 and 1, I would see that, oh, I'm not going to use that one. I don't care about that particular problem or that particular critical value. Okay? So now the next thing we're going to do is we're going to plug these numbers into this function. Now in this case, I'm not going to show my work for how I calculated these. I don't really care if you guys show work because you can use a calculator to do this, and it would make your life a lot easier if you did. That's not important to me. So I'm going to go ahead and put my answers up here. And there's our answers. And then step 4, we want to actually go ahead and determine what the absolute min and the absolute max are. And what they are is they are the y values that are the largest, so and the smallest. So the largest y value is 3. So the absolute max is 3. And the absolute minimum is 0. And there you have it. Okay. Now you could write these as points. So for instance, you could say, instead of writing what the absolute min and max are, we could write it as you have an absolute minimum at the point -2, 3, and you have an absolute maximum at the point -1, 0, and 1, 0. Okay, so that's another way to write it. Now technically just the y values are the absolute extrema, but you can write it as a point, and I'm kind of curious how they do it on this test, so you guys can just kind of be prepared for what you're... It doesn't really matter. This is like a free response test, but they write it as a point. But we're not doing multiple choice, so it's all good. It's just free response. So however you guys want to write it is fine with me. So there's one for you, and I'll let you guys handle that one on your own. All right, let's go ahead and take a look at number 9. And number 9 is another new question. It says, for each problem, find the value of C that satisfies the mean value theorem. 1 point for finding the derivative, 1 point for calculating the difference quotient, and 1 point for solving for C with your work. shown. Okay, so let's go ahead and see what we can do here. All right. So when you're trying to do the mean value theorem, the first thing that we talked about is you want to make sure that it's continuous on the closed interval and differentiable on the open interval, because you're only allowed to do the MVT if those things apply. But once again, on this quiz, you don't need to do that on this quiz. Why? Because once again, we did that in problems 1 through 6, and we don't want to spend more time. So I promise, whatever problem I give to you, the mean value theorem will apply. Okay? So let's go ahead and move on to the second step here of doing the mean value theorem. All right, so the first thing I can recall after that was we went ahead and we found out what the endpoint values were. So what's y of 2, and we also want to figure out what's y of 0. And after we figure those things out, we're going to do y of 2 minus y of 0 over 2 minus 0 to find our difference quotient. Okay, so let's go ahead and plug in our numbers here. We have negative and then 2 squared plus 4 times 2 minus 5. And that would give me negative 4 plus 8 is 4 minus 5 is negative 1. And the next one here would be just negative 5. All right, so plugging that into our difference quotient, we're going to have negative 1 minus a negative 5 over 2 minus 0, which is going to give me 4 over 2, which is 2. All right. Number 3, we need to find our derivative. The derivative is negative 2x plus 4. Number 4, we're going to set these things equal to each other. So I'm going to take my 2 from this thing, and I'm going to take my derivative from this step, and we're going to set them equal to each other, like so. And there's my answer. Okay, so once again, how are you going to be graded on this particular problem? Let's review real quick. I had a couple things that I had listed here. So 1 point for finding the derivative, 1 point for finding the difference quotient, 1 point for solving for C with the work shown. So coming back here, you would get 1 point for showing your work here on calculated difference quotient. You would get 1 point for finding your derivative, and you would get 1 point for finding C. But once again, you do have to show your work for these things. No free problems with no work shown. Number 12, I'm going to go ahead and let you guys do that one on your own, and then we'll move on to numbers. All right, so for number, okay, I'm going to be inserting number 10 and 11 here, so the numbering might not match on the video to the study guide that you had, but just so you know, this is your number 10 and 11, but after that, after I get to number 11, the numbers might not match anymore in the video, but same problems anyway. Because I wanted to insert me doing numbers 10 and 11 also, just to kind of give you guys a little bit extra practice with these problems here. So let me do number 10. So the first thing I'm going to do is I'm going to do my y of b minus y of a over b minus a, where that's my a and that's my b. And after that, I want to set that equal to y prime and solve for x, right? So let's go ahead and do the y of b. What does y of b equal? B is 1, so I'm going to be plugging 1 into the original function here. And that looks like I get negative 2 as an answer. Now I want to find y of negative 1. That's the a value. All right, and that's going to give me Let's see, negative 1 minus 1 is negative 2 minus 2. That's negative 4, I believe. And so if I were to plug the values in up here, y of b was negative 2. Y of a was negative 4. And simplifying, well, we're going to set that equal to the derivative, which is 3x squared minus 2x. And now I'm going to simplify this here. That's going to be negative 2 plus 4, which is 2, over 3. That's 2/3. I think I realized I just had a mistake. This wasn't negative 2. This was negative 1, which means that this bottom number here is going to be a 2. All right, and then reducing that, I get 1. All right, now I'm going to minus 1 on both sides. Now there's two methods that you could try to solve this. One is the box method for factoring. The other method is the quadratic formula. I'm going to go with the quadratic formula this time, just because you will see some problems where factoring doesn't work. Quadratic formula always works. I just don't typically like to use it because it's kind of a pain in the butt to me. It's a lot of work, but it's that on these types of problems, you can expect that you'll see a quadratic formula only problem. So I'm going to recommend quadratic formula for these, okay? But if you want to try factoring, you can. Like on this one, for instance, I'm pretty sure it would factor. But the next one after this won't, so I want to just kind of get you used to it. So to solve for x, we're going to do the quadratic formula. That's negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. The b value is negative 2. The a value is 3, and the c value is negative 1. Okay, so I've got 2 plus 4 and 2 minus 4 over 6. Running out of space, so I need to erase. So if you need to write the stuff down, go ahead and do that, but I am going to be erasing here. So I have 2 plus and minus 4 over 6. That's going to split up into 2 plus 4 over 6, which is 6 over 6, which is 1, and 2 minus 4 over 6, which is negative 2 over 6, which is negative 1/3. Now, those are my two answers, but we only want to include answers that are actually on this interval here. Now, technically, both of them are on this interval. 1 is there, and so is a negative half. Negative half would be somewhere in between. But just so you guys know, when you're doing the this mean value theorem, you don't include the endpoint ones. The reason for that is because we want it to be continuous on the closed interval, but differentiable on the open interval. In other words, we don't want to include the endpoints for the derivative part. So we don't include the endpoints in our final answer, and we're only going to include the one that's in the interval, not on the outside. Okay, so there's that. Let's go ahead and take a look at another one. All right, so here we go. Let's do another one. We need to find out what is f of 3 minus f of 1 over 3 minus 1, and we want to set that equal to the derivative so we can solve for x. All right, so let's find out what f of 3 is, and let's find out what f of 1 is. To do that, we just plug them into the original function up here and work it out. So plugging them in and simplifying, we get 3 and negative 3. So working this out now, we'll have 3 minus a negative 3 over 3 minus 1 equals, now we want our derivative. There's that. Let's simplify this. 3 minus a negative 3 is 6. 3 minus 1 is 2. 6 over 2 is 3. And then we're going to move the 3 over to the other side, so it is equal to 0. Once again, just like the last problem, I'm going to use the quadratic formula. Here we go. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Minus 36. I get the square root of 28 there. All right. So now I'm going to take the square root of 28. A little review on how to do square roots. If you haven't seen it in a while, you look for what times what makes 28. And you keep breaking these numbers down until you can't break them down anymore. So 28 is 2 times 2 times 7. And for every pair, you can write that number on the outside. So we have negative 8 plus and minus 2 square root of 7, negative 6. Next, we're going to go ahead and reduce these 3 numbers. So what goes into 8, 2, and 6? Well, all of them can be divided by 2, but we typically also don't like having a negative on the bottom like that, so I'm going to divide everything by a negative 2. And that leaves me with 4 plus or minus 7 over 3. Now, we want to make sure that these answers are both on the interval that we're given here. So I need to figure out what is 4 plus the square root of 7 over 3. And I also need to figure out what is 4 minus the square root of 7 over 3. Now, if you want to get out a calculator and calculate this out, you can figure out what those are. So 4 minus the square root of 7 divided by 3 is 0.451. And then 4 minus, actually I take that back, that's the subtraction answer. 0.451. And then we'll do the addition one as well. And that one's 2.215. So, are both of these on the interval? This one is not, but this one is. And so this is the answer we would choose. Okay? Sometimes they'll both be on the interval and you would include both answers. Okay? But in this case, only the 2.215 is somewhere between 1 and 3. All right? There you guys go. Let's move on to the next one. 11. It says the table below provides selected values for the differentiable function f on the interval from negative 3 to 5. Number 11 says, is there a value c on the interval for which f prime of c equals negative 2 on the interval? I see there's a typo there. I need to fix that. It should say negative. No, never mind. It's not a typo. My bad. 2 to 5. Justify your answer. All right, let's check it out. All right, so let's see. Is there value c? So what we would do first is we want to, first of all, recognize that this function is differentiable on the interval -3 to 5. And if it's differentiable, we can say it's also continuous. Now, you don't have to do this on your test. I'm just making a note of that there. I'll show you guys what I want to see on your quiz. But first of all, what you guys are going to want to do is I want to see this set up here. Since f is differentiable on 2, 5, that means we could say there is a C such that f prime of C is equal to f of 5 minus f of 2 over 5 minus 2, and it's -2. Okay. Now, it's only going to be true if this actually does come out to be the case where these things are actually equal. If not, then I would go back and I would change my answer, say no. But for now, I'm going to assume that it's going to work. So f of 5 is -4. F of 2 is 2. And -4 minus 2 is -6. And 5 minus 2 is 3. And -2 equals -2. And there it is. Okay, so what's kind of important here for getting your credit on these questions is you're saying, first of all, you're justifying the fact that you're allowed to use the mean value theorem right here. Okay, you're saying since f is differentiable. Now, you don't have to say it's continuous, because if you say it's differentiable, that implies it's continuous. So if it's differentiable on the closed interval from 2 to 5, then now usually when we do this, I've been using open intervals. You can say, though, it's differentiable on a closed interval, and that's just more powerful, because if it's differentiable on the closed interval, then it has to be differentiable on the open interval, and that's what they told us up here in the directions. So since the function is differentiable on that interval, and by the way, why am I saying it's differentiable on 2, 5 when the instructions tell me it's differentiable on -3, 5? Well, if it's differentiable on -3, 5, it's also differentiable on 2, 5 because this interval is inside of this interval. So if it's differentiable on this entire interval, it has to be differentiable on this interval. But why do we want to look at just this one now? Because that's the one that the problem is asking about. It's only asking about as we go from 2 to 5. But anyway, that's a lot of extra information. Let's back up and get back to the basics. So right here, you're just justifying the fact that you are allowed to do the mean value theorem, which is this little statement right here. So from there, you would need to actually show your work on how to get there. Now, these problems here are typically worth about, I would say, 2 points. You would need to have this statement here. And you would, well, I put 2 points there. That would be like worth 1 point having that statement. And the second point would be this, but it's the part that takes you all the way to the end. So basically you start here and then you take yourself all the way to the end where you prove that yes, that difference quotient does equal -2. So, and just to remind you guys, just kind of bring you back to what we've learned. What have we been learning? The mean value theorem tells us that the instantaneous rate of change is equal to the average rate of change at some point along the curve. Okay, and since the average rate of change from 2 to 5, which is represented by the difference quotient, does in fact come out to be -2, that means the instantaneous rate of change has to be -2 somewhere on that interval. Okay, but once again, what do you need? I need your hypothesis to be satisfied, that it's differentiable, and then I need the work of the difference quotient and showing that they actually come out to be equal. All right, now let's go ahead and take a look at the next one. The next one is different. Got to pay attention to subtle details. You'll notice that on number 12, it doesn't say f prime, it says f. Okay, And I'm including something old on purpose, and the reason I'm doing that is because the questions seem very similar, and yet they are very different questions. And the only way the questions look different, as you can see when you compare them, is that this one is an F and this one is an F prime. You got to pay attention. This is an MVT problem and this is an IVT problem. Okay, so keep that in mind. All right, so how this thing works is when we're talking about a y value and not a derivative, it's an IVT problem. What you want to do is you want to make sure that this y value that they give you is actually in between the y values for these x's. So let's take a look at them. Here's those x's and here's those y values. Is this number, -2, between 2 and -4? Yes, it is. So there we go. We're good to go. Since the function is differentiable, it's continuous. And if it's continuous and we're going from a y value of 2 to a y value of -4, there has to be some point along that way in which it crosses a y value of -2. So here's how you word your answer. Since f is continuous, that's important to say that, and goes from 2 to 5 on the interval. I'm sorry, my bad, let me back it up a little bit. What goes here is the y values, and goes from 2 to -4 is what I meant to say. 2 to -4 on the interval of 2, 5. Now that we get that, there must be some x value c such that f of c equals -2. Okay, now that's the intermediate value theorem. This is proving that the slope has to be something in particular on the interval, but this one over here is proving that the y value has to be something in particular on the interval. This one is the MVT, this one is the IVT. This one's about derivatives, this one's about y values. This one only requires continuity, this one requires continuity and differentiability. Okay. For this one, there's really not much work to show. It's just really a statement. You do have to do a little mental work and think, okay, is this y value between these y values? But for this guy, you have to set up that little formula and actually solve it out and prove that it works. Which, by the way, if it didn't work, you would say, no, we can't be sure because I don't seem to be getting that number. But anyway, but by the way, they don't really ask questions where it wouldn't work. It's going to work. Otherwise, the question would be, at best, only a lack of certainty. It wouldn't tell you whether it's there or not. Now, for the rest of the problems, I'm just going to do them all because each problem is a little bit unique. What is a critical value? A critical value is an x value where f prime of x equals 0 and or f prime of x is undefined. Now that's what a critical value is. The reason, now the next part of this is why do we care about what those are, is they help us find where either, if your derivative equals 0, that means you have a flat tangent line, and that means that you could have a relative max or you could have a relative min whenever you have a derivative that equals 0. If you have a cusp, you would have the same thing. There would be a relative max here and a relative min here, but in those cases for cusps, your derivative is undefined. So when your derivative is either 0 or undefined, that's an indication that you may possibly have a relative extrema there. It's not a guarantee, because you could end up in a situation like this, for instance, where you have a tangent or a vertical asymptote, in which case your derivative is going to be undefined. But since this thing goes up forever, there is no relative extrema there. It just keeps going up forever. So just because these things are the case doesn't mean you have a relative extrema, but they're nice indicators of where to look for relative extrema. So You don't need to include any of this in that answer. I was just giving you guys a little bit of background to remind you. All right, let's move on to number 14. If x equals c is a critical value, then f of c is a relative extrema. Is that statement true or false? I think that's what we're going for here. All right, and the answer is no. As I just explained on the last slide there, that's false. You could have a critical value, but it's not a relative extrema. If f of c is a relative extrema, then x equals c is a critical value. That is true. Anytime you have a relative extrema, it's either like this, or like this, or it's like this, or it's like this. And in all of those cases, either the derivative is 0 or the derivative is undefined. So this statement is not biconditional. It's true this way, but it's not true backwards, as we saw in number 4. So if it's a relative extrema, it is a critical value, but if it's a critical value, it may not be a relative extrema. All right, so let's go ahead and take a look at the last few sets here. It says use the graph in number 14. Well, it's not number 14 anymore, is it? I'm going to change that to number 16. Let me fix that. All right, use the graph in number 16 to answer the questions that follow. And they also tell us that there is a vertical tangent line at x equals 5. So I'm going to go ahead and draw that tangent line in there right now so I don't forget about it. Here's where x equals 5. And I'm just going to draw a dotted line to remind me that there's a vertical tangent line there. All right, so for number 16, it says, where are the critical values? So as you guys may recall, critical values are where f prime equals 0 or where it's undefined. So let's look for where f prime would equal 0. F prime would equal 0 anywhere where there's a 0, where there's a flat tangent line. Okay, now there would have been one right here. And so we would have said that there's a critical value at x equals 0. But we're not going to say that. And the reason why is because there's no dot there. So we can't say that f prime equals 0 there. Right? So we'll say that there is no place on this graph where f prime equals 0. Right? But another place where there's a critical value is where f prime is undefined, or where a function is not differentiable. Now, a function can fail to be differentiable for one of 3 reasons. It may fail to be differentiable because it's not continuous, or because there's a vertical tangent line, or because, what was the other situation? Oh yes, a cusp. Okay, so a cusp, as you guys may recall, looks like this, right? Vertical tangent line, we know what that is. Continuity could happen in one of 3 ways. F may be undefined, which could be a hole, so you may have a hole somewhere, or it could be a vertical asymptote. That's one thing that could cause a function to not be continuous. Another thing that may cause a function to not be continuous is even though it's defined, it jumps. Or another thing that may cause it to fail to be continuous would be if even though the function exists and the limit exists, those 2 things aren't the same. And so those are our scenarios where a function may fail to be continuous. And if it fails to be continuous, then the derivative won't exist there either. And so we're looking for places on our graph where we have one of these situations over here. Okay, so as you guys can see right here, f doesn't exist, and therefore it's not differentiable at that point. So that would be a critical value at x equals 0. Here we have a cusp. That's another place where a function is not differentiable. So we have another critical value at x equals 3. Here's another cusp down here. So we have another critical value at x equals 4. And then here we have a tangent that is vertical. So that's another critical value, which is 5. And finally, we have an open dot right here at the end, so we can go ahead and include that as a potential critical value as well. All right, I shouldn't say potential. It is a critical value. So there you guys have it. So you can find critical values. It's anywhere where you have a flat tangent line. Okay, that's where the derivative equals 0. Or it's a place where the derivative doesn't exist, which can come from a plethora of possibilities, and I've got quite a few of them listed here. So this thing has a few critical values. Now the next question is asking us, what are the relative minima? That's kind of like the bottom of a valley, okay? So for instance, this would have been a relative minimum if the point had existed, but it doesn't, so we're not going to include that one. The point actually has to exist. This is a relative maximum. So we have a relative max. There's two ways you could say it. You could say the relative max, or min, I should say. Oh, well, they're asking about minimums. So let me back up. We don't want to talk about maximums yet. We'll get to that. There's only one relative minimum. It's right here. So you could say you have a relative min is, and that's the y value of that point. So the relative min of this graph would be -1. You could say, or you could say relative minimum is -1 at x equals 4. So that's the x value. But the actual relative minimum is -1. Okay. All right. Now number 18 is asking a similar question. It's asking where's the relative max, and that would be right there. It's like the top of a hill, if you will. Oh, that rhymes. Top of a hill, if you will. All right, so once again, you could say relative max is, and you're going to put the y value at x equals 3. Now, you don't have to say at x equals 3, because the way the question is asking, it's just asking what is the relative max. But sometimes the question is worded differently, and they ask where is the relative max located, in which case you would say, well, the relative max is located at x equals 3. So I just want you guys to be aware of the difference between what part of this is a y value and which part's the x value. The relative max or min is the y. Where it's located at is an x value, which are, by the way, critical values. All right, and you guys just saw here, I had about 1, 2, 3, 4. I had about 5 critical values, but only 2 of them turned out to be relative extrema. And relative extrema are always critical values, but critical values are not always relative extrema, and that's why not all 5 of those ended up being an extrema. All right, let's go ahead and take a look at number 19. Now, number 19 and 20, when you're looking for maxima and minima, you have some candidates, okay? I'm just going to do 19 and 20 right here. You have some possible candidates for relative extrema, okay? It could happen at the end point, where x equals -3, or this endpoint, where x equals 7. Now, this endpoint doesn't exist, so I'm already going to eliminate that one. Now, the next thing you do is you put all your critical values in there. Well, not your critical values, I'm sorry. Your relative extrema. So your relative mins and your relative maxes. I had a relative max here. That's at 3. And I had a relative min here, and that's at 4. And so what I'm going to do is I'm going to go ahead and put in there all the, this one would have been a relative extrema as well, but it doesn't exist. That one is at -4. So we can kind of include that. It's at 0 actually, so I put it like right here. So at -3, my the y value is 7. At 0, it's -4, but like we said, we're not going to use that one because it's an open dot, just like number 7 was. 3 is going to be 1, 4 is going to be -1, and 7 was, I'm just doing this for the heck of it, it's 3.5, but once again, like I said, we're not using it. So now the significance of this is we're going to look at our table here, and we're going to ask ourselves, okay, which one of these are the highest point on the graph? And as you can see, 7 is the winner, okay? So we're going to say that my absolute max is y equals 7 at x equals negative 3. The absolute minimum would be the lowest point. Now, there is no relative minimum, and let me explain to you why. Now, I know you guys might be thinking, well, Mr. Bailey, the lowest number here is negative 1. Why isn't that the relative minimum? Because this guy, that's the lowest point on the graph, but it doesn't exist. Now, you might think, but doesn't that mean that automatically 1 becomes the lowest value on the graph? And the answer is no, because as you guys can see, look how low this point is. That point is at negative 1. Well, so is that one. But look, there's lots of points below it. So since this point doesn't exist, as we approach that point, we can definitely get lower than that one. Okay, so this one does not exist. There is no relative minimum because what should have been the lowest point doesn't exist. The same thing can happen with an absolute maximum. If you have, if this had been an open dot up here, well, then that would have ruined it. There would have been no absolute max. Now, actually, I don't know if this is a typo or what. I'm kind of curious what my answer key says, but I think I intended there to be a dot here, just a closed dot, because I do see a dot there. I see an arrow too. Now, let's just say there wasn't a dot there. Let's just say it was just an arrow. Well, then that's not a point anymore that is a stopping point. It just keeps going. So if I asked you what's the absolute max here, well, you'd say there isn't one because it just keeps going up forever. There is no absolute max. It gets higher and higher and higher. So I'm kind of curious what my answer key says. I'm pretty sure I intended it to stop there. So I think the answer is supposed to be 7. But since there's an arrow there also, I'm kind of curious. Yeah, so yeah, no, it's still 7. So I think the computer that I used to generate this question just puts an arrow there, and I don't know why it did it, but there's not supposed to be an arrow there. It's just a dot, so it stops at 7. But anyway, that does it for the day, and we'll stop there, and we'll wish you guys luck on your next quiz. See you guys in class.